I'm Jing from Australia National University and NICTA. This work is a collaboration with Peng, Fang, Cheng, Patrik, Haslum, and Brian Williams. This is the overview of my talk. I'm going to introduce the background, motivation, problem formulation, applications, and conclusion. Let's start with the example of evacuation plan. The flood is coming from the top right corner, and we need to evacuate the people from the whole city before the flood blocks the road. In the evacuation plan, we divide the people into several regions according to their locations, and the cars from each region will formulate a traffic flow in the process of evacuation. And in this example, the flows from region A and region B has to share the same main route to escape from the city. And ideally, we want the evacuation plan to be like at the time point, the flow from region B reached the entrance of the main road. The flow from region A has already passed the entrance of the main route. But what's the proper time to let region B to start to evacuate? We formulate the temporal network for this example. The left line is the schedule for the flow from region A, and the red line is the schedule from region B. And ideally, we want that when the flow B reaches the main route, it has to be after the flow A has already passed the entrance of the main route. And the time slack here should not be very large, because the timing the evacuation plan means people's life. Ideally, we want the scheduler to control every node and every constraint, the duration of this schedule. But it's not true in real life. That's why the simple temporal network with uncertainty is introduced. It is the extension from the STN by introducing the uncontrollable nodes and links. In our example, the controllable nodes are the green ones, the start time to evacuate each region. And the red nodes are all uncontrollable, and the red links are uncontrollable. They're called contingent links. For every contingent link, their duration can be any value within its bounds during the execution. But before the execution, we cannot predict that. We only know the bounds. So because of the uncertainties here, the controllability of STNU is very important. The dynamic controllability means that the scheduler or the agent can decide the future of the controllable nodes based on the observation of the past uncontrollable nodes. And this process of observation, decision is a dynamic strategy. Let's see how dynamic strategy works for this example. When the flow A starts to enter the main route, they may send a message to the scheduler like, "Hi, I'm starting to enter the main route now." And after the observation of this time point, which is T, the scheduler decides, okay, 15 minutes later, let's start to evacuate people from region B. So 30 to 35 minutes later, the flow A, the whole flow will pass the entrance of the main road. And 15 minutes plus 20 to 25 minutes later, the flow A start to enter the main route. And the difference between the last two time points is within 0 to 10, which will satisfy the requirement links there. So then we got a feasible dynamic strategy, which is after the observation of time point that flow A start to enter the main route, we decide that 15 minutes later, okay, let's start to evacuate the region B. The most recent research on dynamic controllability is the DC checking or verification algorithms. It can answer the question whether a schedule is dynamically controllable or not in polynomial time. The original DC verification algorithm was introduced in 2001. Morris and the other authors introduced some reduction rules about local and global dynamic controllability. Each reduction rule will tighten the controllable links according to the duration of the uncontrollable links. And by applying the reduction rules repeatedly until no link in the network has to be tightened anymore. And if the network is still consistent, then it is dynamic controllable. And in 2014, they improved this algorithm into a cubic algorithm. There are other methods can solve the same problem. Here is our motivation. By the DC checking algorithm, we can answer the question whether an STNU is dynamically controllable or not in polynomial time. We can even get the dynamic strategy with large-scale problem. But there are still some questions we cannot answer by the DC checking algorithm, like how far is a schedule that is dynamic controllable to not dynamic controllable, and some other optimization question. Here is an example of instead of using a fixed upper bound to represent the uncertainty of contingent link, we use a variable, which is the lower bound plus the delay of the contingent link. If the delay is 0, it means there's no uncertainty in the STNU, which means it is definitely controllable. And when the delay is infinite, then it means it will never be controllable. So what's the maximum value of the minimum delay of which the network is still dynamic controllable is a very important question, because it is a robustness measure for temporal plans or schedules. In order to answer this question, we introduce our problem formulation as a optimization model of STNU under dynamic controllability. In our model, the lower and upper bounds of links are variables, and the whole network has to satisfy the dynamic controllability constraints and some other application-specific constraints. The key question here is how to formulate the DC constraints. In 2004, Wang and Xing introduced a nonlinear programming model. But in our paper, we introduced a disjunctive linear model. One of the reasons why we use a disjunctive linear model is that it allows us to use some more efficient solvers to tackle with the DC constraints. Like, for example, we can encode the disjunctive linear model into a mixed integer programming model by using the binary variables. And our model is strictly follow the reduction rules of the original DC checking algorithm. Because of the time limitation, I'm not going to list all the constraints. Here is an example of how we generate the constraints by the reduction rules. In the reduction rules, if we have a contingent link AC and another time point B, which has to be scheduled before the observation of time point C, then we have to tighten the bounds of link AB in order to tackle with the uncertainty of the contingent link and satisfy the constraints of the link BC. In our constraint model, we are doing the same thing, like only if the value of the lower bound variable BC is no less than 0, then these two constraints will work. And if these two constraints work, it means the value of the bounds here will definitely satisfy the reduction rule there. By using the same process, we can formulate the whole DC constraint model into a disjunctive linear model. Okay. Next, I'm going to talk about the applications of the DC constraint model. The first application is the robustness measure, which called maximum delay under dynamic controllability. I have already introduced that in the motivation part. This application aims to answer the question, what is the maximum value of the minimum delay among all contingent links for which the STNU is still dynamically controllable? Here is the formulation of this application. We maximize the minimum delay among all contingent links, and for every contingent link, the variable of lower bound equals to its original duration, the original lower bound, and the variable of its upper bound equals to the lower bound plus the delay. And for every requirement link, controllable links, it just needs to satisfy the original loose bound constraints, and the whole network has to be dynamic controllable. In this application, we use partial order schedules for RCPSP max problem as the data set, and we compare 3 different ways to solve this problem. The first one is a conflict-directed search called CDRU. It's developed by Yu and Fang and Williams. In the second method, we solve the mixed integer programming model by Groovy, and the last one, we solve the nonlinear programming model by Snopt. Here is the runtime of this experiment. The conflict-directed search have an overwhelming performance. It can solve every test case within several seconds. And the next one is the MIP model. The problem of the nonlinear programming is not only in its runtime, but also in the convergence. Like only 70% of test case can achieve can return an optimal value by a single run of the solver. And we set the current solution at the lower bound and run the solver repeatedly. And then we achieve 93% of test case can get the optimal solution. Besides the runtime, we also compare maximum delay as the measure of robustness versus fluidity and flexibility. Fluidity and flexibility are 2 metrics for schedules, and they compute average time slack or temporal tolerance of the schedules. The aim of these 2 metrics are to predict the robustness of the schedules. So in our experiments, we try to answer the question, how can fluidity and flexibility predict the robustness of the schedule? We look into pairs of partial order schedule generated from the same problem, and one of the schedule have a higher value in flexibility or fluidity. We compute how often is a schedule with an increase of fluidity lead to an increase in maximum delay, which means robustness at the same time. As we can see from the table, 16 to 17% of the test case have a contrary result, which means the schedule with a higher fluidity or flexibility may have a lower robustness in terms of the maximum delay under uncertainty. We also have some other applications in our experiments. Because of the time limitation, I don't have time to introduce them all. But the first one is very interesting. It's called relaxing over constraint problems. It's actually the contrary, question of maximum delay. When we get a schedule that is not dynamic controllable, what's the minimum cost to fix it? Fix means we can shrink the contingent link or to extend the controllable links. And the last application called dynamic controllability with chance constraint is also very interesting because we use probability distribution to represent the contingent link here, which means the constraints of the contingent link is not linear constraints, they are probabilistic distribution. So only the nonlinear the nonlinear programming model can tackle with this application. In the conclusion, As we can see from the applications and experiments, the DC constraint model is a more useful representation than the DC checking or verification process. It can help us to measure robustness of schedules and temporal plans, and it can also help us to solve other optimization problem of a simple temporal network under uncertainty. By the comparison of the solvers, the conflict-directed search is the fastest one, but the MIP and nonlinear programming model can represent more general problems. That is all of my talk. Thank you for your attention.